Okay, here's a solution video for pre-calculus day 5 problem 1, where we're asked to find a projection of one vector onto another. So to begin, I just want to remind us of our first projection problem we saw in IM2, where there was a javelin that was thrown into the ground and then the sun was shining perpendicular to the ground, which created a shadow, and that shadow became our projection. All right, so we got to think perpendicular here. So for projecting this green vector onto the blue vector, what I have to imagine is the sun shining perpendicular to the blue vector, okay? And what's that going to do to the shadow here? Is it's going to cast a shadow somewhere in this direction over here, right? Because the vector is going to cast a shadow over here. Now, it looks like that won't actually fall on my blue vector here. But it turns out, this is a little more complicated, projections can actually fall in the opposite direction of the vector as well. So what we can do is we can actually continue this vector off into quadrant 4. I'm going to do it as a dotted line because it's not actually the vector, it's just in the opposite direction of the vector, right? So it's anti-parallel to the vector, and we can actually have a projection fall there. So I'll draw that for us. Okay, so here is my drawing of the sun casting a shadow onto this extension of that blue vector, okay? So once I do that, basically what you want to do is create an altitude almost here. And then the red, this thick red arrow, represents the projection of the green vector onto the blue vector. So now the challenge becomes, how do we find the components of that vector? So essentially what we need to do is notice that this red vector, okay, is almost in the same direction as the blue vector, all right? Remember, for a vector, we need to have a direction and a magnitude. So it looks like I can probably use the direction of the blue vector and change it slightly to find the direction of the red vector. And then to find the magnitude of the red vector, I'm gonna need to do something with this right triangle, okay? So I think if I find this angle here, I could do trig with this vector, the magnitude of this vector, and I could find the magnitude of the red vector. Okay, so all I've done here is I used the components of the vector to make right triangles and labeled some angles that I think are going to be important here. So I found this alpha, okay, and I'm going to find this beta using the 12 and the 5 and the 9 and the 12 here. So I can just do trig to find those. And then I think what my goal is going to be is to find this vector, this angle, excuse me, here. Let me use a different color. This angle here, I'll call theta, which looks like, to me, it's alpha plus beta because I have vertical angles here. So this part here would be alpha, and then I have to add the little beta sliver. So let's see what the work in that looks like. So just doing some quick calculations, you can pause the video to catch up if you need to. I can find that blue angle theta by first finding alpha and beta. So now that I have that angle, I know I have a right triangle, and I know I have this angle now. So I'm gonna look for its adjacent side. So I'm gonna probably use a cosine, but first I need to find the length of the hypotenuse, otherwise known as the magnitude of that green vector. So since I didn't give it a name, I just called it green vector. So remember, with vectors, these absolute value bars really mean magnitude. And the way to find the magnitude is to do the square root of the squares of the components added together. This turns out to be a special case because we have a Pythagorean triple, meaning that we get an integer value of 13. So a 5, 12, 13 triangle. So that's the magnitude of the green vector, essentially the hypotenuse of my right triangle. So now I can find the length of the projection or the magnitude of the projection. So once we plug everything in, we get this result. So we know that the magnitude of the projection is 3.2. Now our job becomes finding the components of that projection. And what we're going to have to do to find the components of the projection is we're going to have to take the blue vector, flip its direction, and then scale it, okay? So we've got to actually shrink the blue vector to find the red vector. We need to use the blue vector because it's telling us the right direction to go in, except we just have to flip it, and then we just found its length. So we're going to combine those two things and scale this vector. Okay, so I just put this up here to remind us how to scale a vector. So the first thing you want to do is find the length that the vector is right now, all right, or its magnitude. Then what we're going to do is you can actually multiply vectors by scalars to stretch and shrink them, okay? So first what we're going to do is divide it or multiply it by 1 over the length that the vector is now. And what that does is it makes it a unit vector. It makes it have a length 1, which makes it easy to rescale because then all you need to do is step 3, multiply it by the length you want, all right? So once I shrink it down to length 1, it's really easy to scale to what I want. So we're going to apply this procedure to the blue vector, except first we're going to flip the blue vector. So we're actually going to apply this procedure to the opposite of the blue vector. I'll show you that now. Okay, so I tried to write this out in the steps that I'm doing. So basically, what I'm going to do is take the blue vector and flip it. So the way you flip a vector is you just multiply it by a negative, okay? So I'm taking the opposite of the blue vector. This is a vector, all right? I'll show you in vector notation in a second. And I'm going to multiply it by something to stretch it, okay? So first, this is that step 1, or I guess step 1 is to find the magnitude of the blue vector, which I'll show you how to do. Step 2 is to divide by that length. So here's that division. And then you multiply by the length you want, which is that length of the projection that I found over here. So this is all 3 of those steps put into one. Keep in mind, since I have a vector right here, this blue vector, the projection here is going to be a vector. So I'm going to write that in vector notation now. Okay, almost done here. So here I did a quick little calculation for the magnitude of the blue vector. Again, we got lucky. It's a Pythagorean triple. So 9, 12, 15. And then here is everything put together. I'm still just calling it the projection vector. You can call it P if you want or anything else. And so here is the negative of the blue vector, right? So the blue vector was negative 9, 12. If you multiply that by a negative 1, you get 9, negative 12. So this is the opposite direction, okay? And then here is the magnitude I want, right? We know from our calculation over here that the magnitude of the projection should be 3.2. But in order to first make this vector have a length of 1, I have to divide it by 15. So this is step 2 in my procedure, all right? And then this is step 3. And when you put it all together, you can find the projection. And so when you just crunch those numbers, you get the components of that projection vector. So if you plotted all of this together, this would be that red vector here. So you're going to go over 1.92 and down 2.56, and there you go.